X-ray fluorescence is the emission of characteristic, secondary, X-rays from a material that has been excited by bombarding with high-energy X-rays, or gamma rays. The phenomenon is widely used for elemental analysis and chemical analysis, particularly in the investigation of metals, glass, ceramics and building materials, and for research in geochemistry, forensic science, archaeology and art objects such as paintings and murals. Underlying physics. When materials are exposed to short-wavelength X-rays or to gamma rays, ionization of their component atoms may take place. Ionization consists of the ejection of one or more electrons from the atom, and may occur if the atom is exposed to radiation with an energy greater than its ionization potential. X-rays and gamma rays can be energetic enough to expel tightly held electrons from the inner orbitals of the atom. The removal of an electron in this way makes the electronic structure of the atom unstable, and electrons in higher orbitals fall into the lower orbital to fill the hole left behind. In falling, energy is released in the form of a photon, the energy of which is equal to the energy difference of the two orbitals involved. Thus, the material emits radiation, which has energy characteristic of the atoms present. The term fluorescence is applied to phenomena in which the absorption of radiation of a specific energy results in the re-emission of radiation of a different energy. Characteristic radiation. Each element has electronic orbitals of characteristic energy. Following removal of an inner electron by an energetic photon provided by a primary radiation source, an electron from an outer shell drops into its place. There are a limited number of ways in which this can happen, as shown in Figure 1. The main transitions are given names. An LK transition is traditionally called K-alpha, an MK transition is called K-beta, an ML transition is called L-alpha, and so on. Each of these transitions yields a fluorescent photon with a characteristic energy equal to the difference in energy of the initial and final orbital. The wavelength of this fluorescent radiation can be calculated from Planck's law. The fluorescent radiation can be analyzed either by sorting the energies of the photons or by separating the wavelengths of the radiation. Once sorted, the intensity of each characteristic radiation is directly related to the amount of each element in the material. This is the basis of a powerful technique in analytical chemistry. Figure 2 shows the typical form of the sharp fluorescent spectral lines obtained in the wavelength dispersive method. Primary radiation. In order to excite the atoms, a source of radiation is required, with sufficient energy to expel tightly held inner electrons. Conventional X-ray generators are most commonly used, because their output can readily be tuned for the application, and because higher power can be deployed relative to other techniques. However, gamma-ray sources can be used without the need for an elaborate power supply, allowing an easier use in small portable instruments. When the energy source is a synchrotron or the X-rays are focused by an optic like a polycapillary, the X-ray beam can be very small and very intense. As a result, atomic information on the submicrometer scale can be obtained. X-ray generators in the range 20 to 60 kV are used, which allow excitation of a broad range of atoms. The continuous spectrum consists of Bremsstrahlung radiation. Radiation produced when high-energy electrons passing through the tube are progressively decelerated by the material of the tube anode. A typical tube output spectrum is shown in Figure 3. Dispersion in energy dispersive analysis. The fluorescent X-rays emitted by the material sample are directed into a solid-state detector which produces a continuous distribution of pulses, the voltages of which are proportional to the incoming photon energies. In wavelength dispersive analysis, the fluorescent X-rays emitted by the material sample are directed into a diffraction grating monochromator. The diffraction grating used is usually a single crystal. By varying the angle of incidence and takeoff on the crystal, a single X-ray wavelength can be selected. The wavelength obtained is given by the Bragg equation, where d is the spacing of atomic layers parallel to the crystal surface. Detection and energy dispersive analysis. Dispersion and detection are a single operation, as already mentioned above. Proportional counters or various types of solid-state detectors, g.e., silicon drift detector (SDD), are used. They all share the same detection principle. An incoming X-ray photon ionizes a large number of detector atoms, with the amount of charge produced being proportional to the energy of the incoming photon. The charge is then collected and the process repeats itself for the next photon. Detector speed is obviously critical, as all charge carriers measured have to come from the same photon to measure the photon energy correctly. EDXRF detector types vary in resolution, speed and the means of cooling. Proportional counters with resolutions of several hundred EV cover the low end of the performance spectrum, followed by pin diode detectors, while the C, G, and silicon drift detectors occupy the high end of the performance scale. In wavelength dispersive analysis, the single wavelength radiation produced by the monochromator is passed into a photomultiplier, a detector similar to a Geiger counter, which counts individual photons as they pass through. The counter is a chamber containing a gas that is ionized by X-ray photons. A central electrode is charged at plus 1700 V with respect to the conducting chamber walls, and each photon triggers a pulse-like cascade of current across this field. The signal is amplified and transformed into an accumulating digital count. These counts are then processed to obtain analytical data. X-ray intensity. The fluorescence process is inefficient, and the secondary radiation is much weaker than the primary beam. Furthermore, the secondary radiation from lighter elements is of relatively low energy and has low penetrating power, and is severely attenuated if the beam passes through air for any distance. Because of this, for high-performance analysis, the path from tube to sample to detector is maintained under vacuum. This means in practice that most of the working parts of the instrument have to be located in a large vacuum chamber. The problems of maintaining moving parts in vacuum, and of rapidly introducing and withdrawing the sample without losing vacuum, pose major challenges for the design of the instrument. For less demanding applications, or when the sample is damaged by a vacuum, a helium-swept X-ray chamber can be substituted, with some loss of low Z intensities.